Quadratics, domain and range. This question models a rock thrown from a bridge. Graph the equation and find the domain and range. So this equation here shows what point in time a rock is in reference to the ground. I've written in X and Y. Normally these questions are written as HT, as in time affects the height of the rock, 10 minus t squared. So x being our t. Now I wrote it as y and x so that it would be easier for us to graph. The original equation should look like this though. The height of the rock is dependent on how far in time since the rock has been thrown. Okay? So in order to solve this, we're going to make a table. You guys have done this before. But in this table, instead of like, remember when we're just choosing arbitrary numbers, we'll actually have a good idea of what numbers we need to choose for this. The reason being is, at what point in time, if we're measuring from when a rock is thrown, what would be our starting point in terms of time? So I've written it as x and y, or in other words, time and height. When you throw a rock, what point in time is that considered in terms, let's say it's in seconds? Zero, right? The rock is in your hand at that point. As soon as you throw it, time starts to pass because we're measuring from when the rock is thrown. So the starting point of this rock is 0. Then we're going to measure in seconds, 1, 2, 3, 4, and it's going to give us the height at this time. So we're going to plug these values into this equation here. So height when time is 0 is equal to 100 minus 4 times 0 squared, which is going to give us what for height? 100. So this rock starts, we'll say 100 meters or feet above the ground. The next thing we solve using our function notation is the height after 1 second has passed since we've thrown this rock. That will give us 100 minus 4 times 1 squared. 100. 1 squared is 1 times 4 is 4. Our height is now 96. So we're noticing that the rock is starting to decrease in height. It's falling to the ground. Our height after 2 seconds will give us 100 minus 4, 2 squared. 2 squared is 4 times 4 is 16. 100 minus 16, 84 seconds. Okay? We're going to continue this pattern because we're trying to graph this. When or at what point will we figure out when we need to stop plugging numbers into this?
When you reach 0 or past 0.
That's right. The height of the rock essentially can only hit the ground, right? It's not some type of comet flying through the earth. As soon as they hit the ground, we stop. We know that's where we're going to end. So I'm going to continue using these numbers and plugging them in until we find a height of 0 or at least a negative. So to continue with this, height at 3 is 100 minus 4. 3 squared is 9 times 4 is 36. So 100 minus 36 is going to give us 64. Is that right? I think that's right. Height at 4. 100 minus 4 squared. That's 16 times 4, which is, I think, 64. Yep. I'm assuming my math was right before. We're at 36. So if you're noticing, it's falling faster and faster as time passes. Our height after 5 seconds is 100 minus 4 times 5 squared. 5 squared is 25 times 4 is what? Perfect. At what time does this rock hit the ground? 5 seconds. Okay. So each of these things we found here are actually coordinates on a graph. We're going to plug all of these in, and then essentially we're going to fill in the space between them. We're going to connect the dots. So the next thing I need to do is bring up a graph here. Scale of 10s, perfect. Oh, not quite what I wanted. That's a scale of 5. Okay, I'll bring this one in. And I'll just add zeros to it. Keep going. Okay. Remember, we said that this has to start at 0 when x is equal to 0. So that means our starting point, we said, would be at 100. We're just going to make this a scale of 10. Okay. The second coordinate we found was at time of 1, and that was 96. So that's roughly here when we go to plot it. After 96, I guess we should zoom out a little so we can see everything. There we go. After 96, we found 84. Oh, geez. I'm going to have to zoom in. All right. At 2 seconds, we were at 84. At 3 seconds, I think we were at 64. So the time, it's starting to speed up. It's dropping faster. 4 seconds was 36. And at 5 seconds, this had hit the ground. So here's the graph we're working with. Okay, that's our parabola. Now, remember we said that it had to start at 0. And we knew when it hits the ground at 5 seconds. That's at 5 and 0. Okay? Our starting point was actually 0 and 100. So, what we're going to do here, the domain and range actually has restrictions on them. Even though if we were to continue this parabola, we know it would be symmetrical the other way. It would look something like this. But we can't go back in time. So we actually have a starting point. And the rock actually stops falling. It stops falling when it hits the ground. Okay? So what we're going to do is I'm going to actually kind of box this. This parabola exists. Do it in blue here. It exists down this line in this boxed area. Okay? Because I was able to encompass this entire parabola in a box, it shall help me with my domain and range. First of all, let's talk about the domain. The domain started at where? What time did it start at? 0. At 0 seconds. And when did it finish falling? Oh, I drew that. Yeah, that's fine. Okay. So, we know our domain, x has to be between 0 and 5. So the way we write this is we say x is greater than and equal to 0, but less than and equal to 5. So when we go to write the domain, because it's a continuous function, we have to start with xer. But this is going to end up being our parameter. X is between 0 and 5, or x is greater than and equal to 0, but less than and equal to 5. We need to write it in this function notation. It needs to look this way when we write it out. Okay? And the range. Well, what is the highest point, or where does it start falling from? Yeah. And at what point does it hit the ground? When the height is 0. Okay? So again, this is going to be written very similar to that. Y has to be greater than and equal to 0, but less than and equal to 100. So when we go to write our range for this function, because it's continuous, we start with y is the element of all real numbers, such that, and in this case, y has to be greater than and equal to 0, and less than and equal to 100. That is the domain and range of a function that has restrictions. Okay? I boxed it out to help me make sense of where this only exists.